So given that a lot of you probably haven't had econometrics yet, you may struggle with the concept of what a regression is. And this will make reading some of the papers a little bit difficult. You might not completely understand what's going on in the state assignment on regression and do files. So I want to make sure you have at least a base level understanding of what's going on here. It really is quite simple. And I'm just going to go over very simply the calculations that are going on when you ask Stata to estimate a regression equation. So first off, let's do an example. I recently downloaded data on Japanese soccer teams, the revenue they earned in 2020 for the Corona season, and I matched that, or merged, I should say, I merged that data with the population of the cities that the teams are in. So here the revenue is in millions of yen. The populations are not 2.59 people. This is also millions of people. So that first row is 2.59 million people. And this is just a small snapshot of the first 10 observations. I have a lot more. I have 56, I think. As you can see, Kashiwa is missing revenue data. I don't know why, but it was missing in the report that I downloaded from the league's official website. And this is just a common issue you come across with data. It's almost never complete, perfect, or without errors. So everything I'm going to do here is going to omit Kashiwa because we don't have data on the revenue. But what I wanted to look into here was a thought experiment that I like to have a lot, which is, well, what would I do if I wanted to start my own soccer team? Sort of a lifelong goal of mine is to own a soccer team. And so I often like to fantasize about what city I would go to, what would make a good candidate for a successful and or hopefully profitable soccer team. And so here I'm just going to do a little thought experiment looking at population and how the population of a city affects the revenue of their soccer team. Now this is very simple. You want to consider a lot of other factors, but I'm going to walk through this thought experiment with you. And actually it's going to become an actual experiment just to give you an example of a simple regression and why we might want to estimate one. So if I plot the data, these are all the teams. Each dot is a single team in 2020. On the x-axis here, I have the population of the city the team is located in. And the y-axis, I have the revenue in millions of yen. So you can see there's a clear positive relationship between the size of the city and the revenue generated for the team. Now, if you've read the first couple chapters of Dr. Fort's book, you understand why this is the case. Or, if you're just a good student of economics, it should be pretty obvious. The bigger the city, the more fans can physically attend. But more importantly, when it comes to revenue, the more eyeballs are watching TV screens or computer screens, which can then be sold to advertisers, which is where the real money comes from. So this is as expected. It's not a perfect line. There are some outliers, right? We have some observations up here that don't fall into this cluster, and we have some observations over here kind of by themselves. So it's not perfect, but you can see that there is a positive relationship. Now let's say we wanted to build a function, a simple function, to represent this relationship as closely as possible. Now let's say we think a straight line or a linear relationship is fitting for this data. Maybe we estimate a line like this. This is actually the regression line that we are going to estimate here. So the goal of regression, or what we're going to call here ordinary least squares, it's the method we use to estimate this line. The goal is to find the line that best fits the data. And we'll define in a little bit what we mean by best fits, because there's a couple different ways, actually there's many different ways, you could define what it means to fit the data. We're going to use one specific definition, because that definition will be the most accurate, or I should say it will lead to the most accurate estimation of this line. Now, why do I want to estimate this line, going along with my daydream of owning a soccer team? Well, I have access to some farmland in Toyota. And so I'm thinking, if I was to estimate the revenue I might earn from owning a soccer team in this city, the worst case scenario might be reflected by the 2020 season, because in that season there were many games where fans were not allowed to go to the stadium. Many advertisers around the world stopped paying for ads because they're afraid people weren't buying things anymore. So if I can estimate the relationship between the population of a city and the revenue the soccer team earns during a really bad year, maybe I take that and I plug in the population of the city I'm interested in, Toyota, wherever it is down here. I think it's somewhere in here actually. And this will give me a good estimate of what I would expect to earn in revenue for having a soccer team in Toyota during a pandemic. Maybe we take that as our worst case scenario. So the equation we're going to estimate is a straight line. So here I'm modeling it as y as a function of x. Beta naught and beta 1 are constant numbers, and that's what we need to figure out. Beta naught is the intercept. Beta 1 is the slope. Now you see I also have a plus epsilon. You might be wondering, why is there another constant? There's two constants there. Epsilon measures the error. So as you can see, if we go back, ignoring the red line, let's just look at the data. Looking at this data, there is no straight line that every one of those dots fall on. So if there's a true relationship between population and revenue, right, given any possible city I could have, even ones that don't exist in this data set, if there's a real relationship that exists, it's not going to be a perfect straight line. Look at these dots. They don't line up. And so the epsilon term here measures the error, the amount of difference for each y, which here is revenue, given x, which is population. So epsilon is measuring the difference between the actual observation y and that line, which is represented by beta naught plus beta 1x, or what I'm calling there the expected value of y given x. So if you don't know how to read that e, that's how we read it. E is the expectation operator. So we read that as the expected value of y given x. So you tell me x, this line will tell you what you should expect y to be. In terms of our example, you tell me the population of the city. This line will tell you what we expect revenue to be during a pandemic season, or to be very specific, during 2020. Now, why should we have epsilon? Well, as I just showed you, the relationship is not a perfect straight line for sure. But another reason is we might have omitted variable bias. That is, there are variables other than population that affect the revenue of the team. Is there an international star on the team? What league is it in? Actually, the data I showed you is across 3 different leagues. So we've got 2 minor leagues in there as well. Since I'm not controlling for those variables or that information in this line, some of the teams are going to overperform if they're in small cities but in the top division, or underperform in terms of revenue, according to that line, if they're in large cities but in lower divisions. Because the lower divisions get less revenue, less eyeballs, and typically lower ticket prices, and less attendance. Another reason is measurement error. These revenues are estimates. They might not be perfect. So it might be that our y variable has a little bit of error to it. I imagine it does. Same thing for population. Population are estimates. It might have been estimated from a survey that didn't literally count every person in the city. And so that might be off a little bit. So even if there's a true relationship that is a straight line, we might not be perfectly measuring our y and x. And so we might imagine there's some error then. Lastly, the functional form might be different. As I said, the straight line does not perfectly fit that data. It looks pretty good for most of it. But if the true relationship is not a straight line, and yet we're estimating the straight line that best fits the data, well, we're going to have error because the relationship is not really linear. For example, looking back at our data, if I use a quadratic relationship, add some curvature to that function, actually, this probably fits the data a little bit better. It captures quite nicely those outliers on the end. By the way, as you can imagine, those are both 2 Tokyo teams. So if this is the true relationship, and yet I'm estimating a line, obviously I'm going to have some error. Now, when we estimate our regression, we will get numbers for beta naught and beta 1, and then the predicted value, plugging in any x to that line, will give us a y, and that'll be the predicted value. We'll call y hat. And actually here you can see we put a hat on beta naught and beta 1 as well. When we do that in the notation, this is referring to the values that we've estimated. So it's no longer a theoretical relationship. Beta naught hat refers to the actual number we get when we estimate this line. Beta 1 hat is the actual number we get when we do this estimate. And y hat is the actual prediction of revenue given x, given our population. Now our predicted y is not going to be perfect. We're going to be off some. The amount we're actually off by, once we estimate the line, we notate that as E, which is similar to epsilon. For observation I, so I'm writing EI here. This is the actual error between the line we estimated, not the true relationship, the one we estimated, and the actual data point. So here what I'm saying is EI will be the difference between the actual revenue of a team and the revenue our line would predict once we've estimated it. The difference between E and epsilon is, again, epsilon is talking about the true relationship, or the difference between the actual revenue and the expected revenue of Y given X from the true relationship, the true line. So let me try to be clear, because I know that's confusing at first. So imagine here we have a true relationship. You see the true line is solid, expected Y given X, and it equals beta naught plus beta 1 times X. Now let's say if we have all the data in the world, this is actually the relationship that exists. So there is some true relationship between population of cities in Japan and the revenues that can be earned, and it's represented by this solid line. Now we don't have all the data. For example, you saw that Kashiwa was missing revenue for one. And every city in Japan doesn't have a soccer team. So I can't measure for a lot of in-between cities what revenues would be. For example, Toyota doesn't have a team. They do have a stadium that was built for the World Cup, and the neighboring city, Nagoya, sometimes has their soccer team play there for big games, but Toyota itself doesn't have a team representing the city. So we're going to have an incomplete data set when we estimate our line, and maybe we come up with something like this dashed line. You see the difference is there's a beta naught hat in the intercept here, right? Because this is what we estimated. This might be the true intercept of the relationship between population revenue, but this is the one we estimated because we don't have all the data. Or we have measurement error, or both. So we want to get as close as possible to that solid line, the true relationship, but in reality, we're not going to. We're going to have some error. Our line is not going to be the perfect true relationship. So as you can see what's being illustrated here, if you look at X6, this is, for example, the revenue of row 6, let's say, the team that's in row 6. And according to its data point, the revenue is actually Y6. The difference between that data point and the true relationship is epsilon 6. So if we were to estimate the true line, we would still be off for this team because of the reasons previously stated. Now, we don't estimate the true line, we estimate a line very similar to it, very close as we can possibly get, right? That's the goal. But we actually estimate that dashed line. So that'll be the one that we actually estimate from Stata. We don't know the true relationship. The point is we're trying to guess it, or estimate it, I should say. But we don't actually ever see it. What we see is the dashed line. And so the difference between our prediction from our line and the actual data point, we call that E6. So we refer to that term as the residual. It's the leftover revenue that's not explained by our model. Because our model would predict Y6 hat, as you can see over here on the left. We would predict this revenue, but in reality, the revenue was higher. So the difference between what we would predict in reality, we call that the residual, and we label that with an E. Now, why is this important? It is just notation, but there is meaning, as you can see. When we put hats on our betas, it's not the same thing as when there's not hats. We're actually talking about an estimated line versus the true line that we're attempting to estimate. And so the epsilon is the true error, whereas the E term is the residual we get from our estimated line. So it's good to be very strict with your notation so that you're very clear with what we're referring to. Okay, so within units of observation, so here I have 56 teams, we have in different equations. So we have one of those equations for each row of the data, or for each team. Another way to write this is the difference between the revenue Y and the error that we're going to get, the residual I should say, is our Y hat. We can define that as Y hat. As I just showed in the previous graph, the difference between Y and Y hat is the residual. So all we're really saying here is our Y hats, or our predicted revenues, will simply be the line we estimate once we plug in the X values. So for team 1 or row 1, I plug in its X1, I use these predicted betas that we will have eventually, they will be numbers, and I'll get my predicted Y hat or my predicted revenue. Now notice here for any team in, for any row in, we could say, notice that the coefficients don't vary across observation. So the X's will change, the population of the city will change, the Y will change, the residual will change. But beta naught and beta 1 do not have in subscripts. They don't change per row. Those are the same for every team because that is the intercept and slope of the line. Everything else does vary. Everything else is team specific. But we're assuming a common relationship. Now, as I said before, we can add other variables here, right? We might want to know what league these teams are in. That's going to matter. We might want to know how many international stars or national team players are on each team. That draws a lot of fans and sponsorships. We might want to know the probability of the team winning a championship. If there's no hope, the fans might not show up. On the other hand, if they've won every year for 10 years in a row, fans might not show up because it's boring. Now, if you read the literature, you'll find that it depends on what you're talking about. That's kind of true for Americans, I believe, but not true for Europeans, at least when it comes to soccer. So if we wanted to do that, we could use the same notation. It's a very similar process to estimate a slightly larger model. So here maybe x2 is what league they're in. Maybe we can have another x3 with how many national team players there are, and so on and so forth, up to xk. So for any k number of variables, we could just add more variables linearly, and nothing really changes. We can get the same interpretation of our model. We estimate it the same way. So you can compactly write this, if you would like, as a summation of betas multiplied by x's. And we would solve for all the beta k's and beta naught. Now at this point you're wondering, what do you mean solve for these? How do we actually solve for these numbers? Well, we have to decide what we mean by best fit the data. And it turns out the procedure known as ordinary least squares is the best linear unbiased estimate of the true relationship. What that means is, out of all straight line estimates of what this relationship is, using ordinary least squares, what we're getting ready to describe here, will give you an unbiased estimate, meaning we expect it, on average, to be the actual relationship with the least variance. So that is, if we come up with any other criteria for how we should select the coefficients of this line, even if some other criteria is also unbiased, meaning we expect it to give us the real answer, if we estimate both of these procedures 100 times on 100 different data sets, the ordinary least squares will be more accurate more often. That is, it will approach the true relationship with less variance. Now, to truly see that and understand it, you should take an econometrics course. That will be covered. You can prove why that's the case. For here, you'll just have to take my word for it. Okay, so what are we doing? The procedure is to take those residuals for our estimated line, square them, and sum up the squares. This is why we call it least squares. Because once we have, in notational form, the sum of the squares of the residuals, we want to choose the coefficients, the intercept and slope, that minimizes this sum of squared residuals. So we're choosing the beta naught and beta 1 that makes this summation as small as possible. You know, in a perfect scenario, our residuals would be 0. We have a perfect line. All the dots fall exactly on the line, and there's no error. Now that's not going to be the case here, but we'd like it to be as close as possible. So why do we want to do this intuitively? Well, one, it's easy. You'll see it's a very simple procedure. It's just a calculation. And Stata can do it very fast, even if you have millions of observations. Two, the choice kind of makes sense. We're not just trying to get the least residual, the least error in our estimate. We're punishing residuals that are bigger more, because the squared term is even bigger. It's exponentially bigger. So what that does when we choose to minimize the squared residuals rather than just the sum of residuals, well, one, negatives and positives don't cancel out, but two, the bigger the residual is, the further away from the line it is, the more it harms our estimate, the more it influences the coefficients. Actually, that can bring some problems with it when you have outliers, but sort of at a surface level, it kind of makes sense intuitively. Third, when we do this, the coefficients have an interpretation of average responses. So that is, once we get our beta 1, or slope, we can interpret that as saying, this is the average effect on revenues of increasing your population by a small amount. So the slope will tell us on average how much you expect revenues to go up with population. And like I mentioned before, another reason why we like this, it is actually the best linear unbiased estimate, meaning of all straight line estimates, of all different procedures we could come up with to estimate this straight line, this one is expected to give us the true relationship. And if we estimated this over 1 million different samples and looked at how much we were off in each sample, that variance in the different estimates we would get is smaller than any other procedure. So more accurate more often. Think of it that way. All right, so let's get to it. How do we actually do this? Well, according to the equation, the residuals are just the difference between the y values and the predicted value, which is beta naught minus beta 1 times x. So if I square that difference, then that's the residual squared. I can write it like that. So what we want to do then is minimize this expression by choosing beta naught and beta 1. I've put hats on them here because once we choose them, there are estimated values. We want to choose those coefficients to make this summation as small as possible. Well, how do we minimize a function in mathematics? We take the derivative, set it equal to 0, and we're looking for a minimum. When I take the derivative of that sum of squares, the 2 comes down from the exponent, so I have 2 times the expression on the inside. Then we have to take the derivative of the inside. So here I'm taking the derivative with respect to beta 1 hat. And so I got to take the derivative with respect to beta 1 on the inside. That gives us negative xi. So I know it looks messy, but this is just a simple derivative from calculus 1. You're taking the derivative with respect to beta hat 1, or beta 1 hat. We set it equal to 0 to find the minimum. Now, how do I know this function will give me a minimum? Well, we have 2 variables here, so we would have to do some matrix algebra to show you that this function is actually convex, so that whenever you find the 2 coefficients that'll cause this function to be at a point where it doesn't change, that is a minimum, not a maximum. So you'll just have to take my word for it here, but when you take econometrics, you can prove this. Okay, so moving forward, we took the derivative with respect to beta 1 hat, one of the variables, set it equal to 0. We can combine terms. I can multiply through by that xi. We can divide both sides by 2. 0 divided by 2 is still 0, so we just get rid of that. And then this is just a sum of sums, so I can distribute that summation sign and solve for beta 1. Now this is just algebra. I'm just rearranging and solving for beta 1 hat. But we're not done here because beta naught is in this expression as well. And we need to solve for beta naught. So we're not finished, but we do have this equation. So what we did is we took the derivative of the sum of squares, which we're trying to minimize. So we set it equal to 0. We took the derivative with respect to beta 1 hat. Now we need to do the same thing for beta naught hat, and we'll get another expression. What we found here is that when we're minimizing with respect to beta 1 hat equals this mess of stuff on the right. The problem is it also involves a beta naught, so we need to know what's going on there. Okay, moving on to doing the same thing for beta naught, starting again with the summation of squared residuals. We'll now take the derivative with respect to beta naught hat, and it looks very similar. We take the 2 down from the exponent, but now when we take the derivative of the inside, it's just the derivative of that negative beta naught, so we get negative 1. Now this time we'll divide both sides by negative 2, because that negative 1 and 2 combine to be negative 2. We get rid of both of them, and here I distribute the sums, and you'll notice when we have a sum from I equals 1 to n in observations of beta naught, which is just a constant, that means we're just adding up n beta naughts. We just have beta naught over and over n times. So instead of the summation, we can just write n beta naught. Now that's going to be very useful because when I rearrange this to solve for beta naught, I'm going to have to divide by that n. But what is the summation of all y's, when there's n of them, divided by n? So here that's saying we're adding up all revenues of the teams in our data set and dividing by the number of teams. Well, that gives you the average revenue, doesn't it? Likewise, I have minus beta 1 times 1 over n times the summation of all x's. Well, that term there is beta 1 times the summation of all populations divided by the number of teams. Well, that's just the average population. So actually, this beta naught hat is really just the average revenue minus beta 1 times the average population. Okay, so we took the derivative of the expression we wanted to minimize, which is the squared sum of residuals. We want to make it as small as possible. We took the derivative with respect to both variables we're trying to solve for, set it equal to 0, and we get 2 equations. So what we have now is these 2 equations, and we need to solve for 2 coefficients. So thinking back to your algebra class, we have 2 equations, and two unknowns. What do? Well, the simple thing to do is just take one. Let's take the simple one for beta naught, plug it in for beta naught in the first one, and we will have an expression that's all in terms of beta 1, and now we can solve for beta 1. Once we do that, we'll plug that beta 1 right back in here, and now we have beta naught. So at this stage, again, it looks a little intimidating, it looks a little messy, but it's a simple algebra problem that you could have done in high school. So let's start with that beta 1 equation. I'm going to first take this denominator and multiply it over here. Okay, and that's what it looks like. I'm going to remove the super and subscripts on the summations because it just gets messy. But they're all the same. They're all summing from I equals 1 to n. Now we'll plug in for that beta naught equation, y bar minus beta 1 hat x bar. And now we have an equation that's completely in terms of beta 1 hat because those x's and y's are given. They're our data. And so if I isolate beta 1 hat, I will get an equation that tells me how to calculate it, given our data. So first I'll multiply this summation of xi's to y bar and to beta 1 hat x bar. Okay, and beta 1 hat x bar becomes a positive because we have minus and negative, right? So that becomes positive. And now we can take this beta 1 hat to the left-hand side so that we get all beta 1 hats on the left-hand side. When we do that, we can factor out the beta 1 hat, and this is what we'll get. And lastly, we just divide by this expression so that beta 1 hat is all by itself. And so here is our equation for how we calculate beta 1 hat. This is something you can do, and you should do actually. Compare this to what you get with Stata. When we do a simple regression, you could actually do this in Excel. This first term here is just taking your x's and y's and multiplying them and adding it all up. That's just a number. Imagine looking at this data in Excel and you just take your revenue and your population and you multiply them both, maybe make a third column, add that all up, and you get this number. Then you take your average revenue, calculate the average revenue of your data set, multiply that by the summation of all the population, or the total population. Over here, you're just squaring all the populations and then adding them up. That's just a number. Here, you're taking the summation of all populations, multiplying it by the average. But again, each one of these four terms is just a number, and then you subtract the terms on top, subtract the terms on bottom, take the ratio, and that's your beta 1. Now, it takes a bit of math to show this. I can send you guys the derivation if you like. It's good to try it on your own. But this can be rearranged, and it's typically written as follows. This is actually the same expression. It takes a bit of work to get there, but this is the same expression. And people like this expression instead of the one I originally derived because there's some good intuition there. You see on the top, we're looking at the variation or the difference between each team's population and the average. We're looking at the variation in each team's revenue from the average, and we're multiplying those two together and adding them up. So this numerator is sort of getting at how much the data is moving. How much is X moving around and how much is Y moving around? And then it's divided by basically this term times itself or squared. So it's kind of like saying how much does X correlate with Y? How much are they changing together? How much is X changing? If we see how much these are changing together, given how much X is changing, that's going to tell us the slope. Well, what does the slope tell us? It tells us how much Y changes when X changes. So there's some good intuition there. That's why we like to write it this way. Again, I'm going really quick. You'll get more details in econometrics, but I hope this is useful. This is just showing that if I give you a set of data, if I give you two rows, revenue and population, this is just a calculation. You just calculate this number. You could do this by hand. And we got this calculation by minimizing the sum of squared residuals. So this coefficient, this slope, will give us a line that provides the smallest possible sum of squared residuals. But we still need to solve for beta naught. So let's take this and plug it in. As you can see, actually we're just going to plug it in right here and we're done. There's no rearranging actually, right? So once I plug that in, it looks kind of messy, but that's what you get. You're just going to take beta 1, whatever that number is, beta 1 hat, multiply it by your average X, subtract that from your average Y, and that's your intercept. So that's again just 2 columns of data, and this is a calculation. If the data set's small enough, you could literally do it by hand. Now, when I do this regression in Stata, this is what gets spit out. We're not going to cover everything here. I'm going to slowly introduce this. Some of you will already understand this. But I want you to, for now, focus on these numbers down here, the coefficients. So revenue is our y variable. The coefficients are talking about our betas. This underscore CONS stands for the constant term. I don't know why they write that and not simply the word constant. I'm sure there's a good reason, but I don't know. That's our constant, so this is our beta naught hat. And population is like our x variable, and its coefficient will be the slope. That's the beta 1 hat. So the way we read this is, for every unit increase in population, which our population here is in millions, we would expect an additional 909 million yen in revenue. Now that sounds like a lot, but that's less than $9 million once you convert it. So again, this was the line that we theoretically were going to estimate, which we did actually here. For us, the y and the x is revenue and population. Plugging in the coefficients, it gives us this equation. And so if I want, this is our red line that I showed at the beginning. Let's show it again. This is the line we just estimated. It doesn't actually intercept here, but if it did, it would do so at 1, 1, 1, 1. You can see it's aiming kind of halfway there between 2000 and 0, right? And the slope is 909. So this is the line we just estimated. Now, given that Toyota has a population, or did in 2020, I believe, of 326,383 people, not a huge city, lots of farms, I could estimate with our regression equation how much revenue I would expect to get in a city of that size with a soccer team during a pandemic year. Because again, this data came from 2020, so these revenues are reflective of having a pandemic whilst operating your soccer team. So all we have to do is plug in that population to this term here, and we have a simple calculation, simple addition. So I remember that our population's in millions, so I'm going to have to move the decimal there. So that's why here I've written it as 0.36. And if you combine those terms, you'll get 1,442, rounding up, million yen. So what's 1,000 million? Well, it's a billion. So that's over 1.4 billion yen. Using the average exchange rate in 2020 to the dollar, that's actually only $13.5 million. Probably not even enough to afford someone like Ronaldo, but you can probably pay for a team. You're just not going to get Champions League quality, right? And so there you have it. That's what a regression is. What we're doing here is estimating that best fitting line to a set of data. And by best fitting, what we mean is we're going to take these residuals, the difference between the actual data points and our estimated line, and this line actually minimizes the sum of the square of all those residuals. So if I square all these distances, add them all up, this line gives us the smallest amount. So using that definition of what is best, we get this line that we can use to estimate how much revenue we would get given a population. We can actually estimate it for populations that don't exist. So you can see there's no teams between 3 and 3.5 million people or having that many people in their city. But we can use this model that we've just estimated to guess a y hat or a fitted value of what revenue might be for a city that size. Now, of course, Toyota wasn't there. It was actually move the decimal down. It was 0.3 million, right? So we're more like around here. But in any case, the point is this model can be used to then make very good guesses about what you would expect in other scenarios. Not only can we use the model to predict what we think would happen in different scenarios, it provides an estimate of the average effects of population on revenue. So if we're looking at increasing a population of a city and you want to know what effect that might have on your revenues, the slope of this line gives you that answer. So think about that in terms of the NFL. The 2 football teams that just moved recently to LA, they were thinking of going from, smaller cities to much larger city. And obviously they did a calculation, probably more complex than this. But intuitively, it's the same idea, right? You go to a city with bigger population, you're going to get more revenue. Now, if you're interested in team location and relocation, there's a lot more going on than simply looking at population. They're also getting cities to play off each other and compete for the teams and offer tax breaks or free stadiums or subsidies. So there's some game theory, there's some negotiation going on there. But this is also at play. And we can use this model to estimate on average what more people are worth in terms of revenue for your team. So that should get you started. That should help you understand what's going on in the regression assignment. Again, this is no substitute for econometrics class, which I highly recommend everyone take as soon as possible. In my opinion, it's the most important class of your economics degree. So whether this was a refresher for you or the first time learning what a regression is, you're now ready to move on to the next video and actually do this yourself in Stata. So have fun.